Hello, welcome to this lecture where I'm going to introduce in just a few minutes what is it about combustion and safety science that could be of use to wildfires. It's a very simple introduction, and unfortunately I will not be able to make you experts on the topic in this few minutes, but what I would like you to do is to find the energy and the motivation to then become an expert through other means, reading books, other lectures, asking questions, etc. The table of contents is I'm going to be briefly talking about bad fires and good fires, the topic of safety, which is affects both of them, bad fires and good fires, and just a few strokes of knowledge on ignition flame spread. Every conversation on fire science should actually point out to its beginning. It started a long time ago, about 1.5 million years ago. It did not start in a fancy, advanced, state-of-the-art laboratory. It happened actually in the wilderness when humans, our ancestors, stopped fleeting wildfires as they've been doing for many millions of years before, and started to go back to it and maybe have some inquisitive play with the flames. At the end, they actually were able to recover the flames, to observe the flames, to manipulate the flames, and master the flames. This discovery, nature invented fire, we humans discovered it. It is considered by many intellectuals as the single greatest discovery in human history. And such is because it led to a completely different way of cooking. It actually allowed different type of development of our physiognomy, gave heating, so we could actually go to places where it was too cold. We could actually have light at night. It actually led to a different type of warfare that will be for bad, and it led to hunting in a different manner. And later by later, they started to start the management of metals and metallurgy and industrial revolution at some point. But there are good fires and there are bad fires. I'm going to talk about the bad fires mostly. You can think about them. It could be a fire in a wild urban interface. Imagine that you are living in a house that is not far from the forest, and the forest is burning with a wildfire, and we are in the house. Then as soon as the fire might be reaching the house, that becomes a bad fire, at least locally, respect to the protection of that home. Or we could actually have bad fires that are happening inside our house. I'm an engineer, so actually most of my knowledge and my work is to protect people and property and environment from fires that happen inside, due to ignition failures, due to all sorts of accidents, overheating accidents, lithium-ion batteries, arson, etc. Um, but the two of them are bad fires. They are examples of these phenomena invented by nature that, of course, smoke is very toxic. There is no such a thing as smoke that is not toxic. Flames hurt people and actually burn homes. Then we have good fires. Let's not forget about that. That's why fire is the single greatest discovery of humankind. We have cooking, not just fancy barbecues, but all types of cooking. And we have heating, which is very nice. And will also take us to places, the internal combustion engine. And then we have wildfires, which I purposely put in between, because some wildfires are bad and some wildfires are good. And that is a philosophical understanding of wildfire phenomena that Paralife and this course, not this module, not my lecture today, but the course of Paralife and the course of your experience in this big project will for sure emphasize in different aspects, different moments, and different people. It's just it is probably something that should be said almost like every day, that not all fires are bad, not all wildfires are good. And it's not straightforward to identify which ones are good, which ones are bad, and why. But it's a question that we always have to ask ourselves. So just let me tell you about something about the bad fires, the ones that are a true threat to our safety. This is a graph of the number of fire deaths in the United States over the last 100 years. It's expressed as the number of fire deaths per 100,000 inhabitants. And you can see that it used to be a very large number, completely unacceptable for society, and it has steadily, almost linearly decreased. It's at a few hiccups here and there, it's always decreasing. So it's a success story. We have dropped by 90%, we have reduced by 90% the number of fire deaths in 100 years. So it's progress, very slow, but there is progress. Two things to say about this. Although this data is from the United States, this data is known to be the same in every single Western country, the UK in particular. The thing is, people have really, or countries, have really poor data sets about fire fatalities inside the building or outside the building. And the United States and the UK are by far the most consistent one, precisely in time. Some other countries are very good over the last decade. Some other countries are very good over the last year. United States and UK are good for a very long time. They're very useful data sets. And the second one is that most fire fatalities, you probably know this, are not actually because of wildfires. Wildfires, thankfully, don't kill many people. They kill very few people, not immediately. They have massive impact in society, in the economy, and the ecosystems, but they don't kill many people. So this plot is referring to people that die because of bad fires inside our homes, not from the outside. However, look at these statistics, that the number of fire fatalities is about 5% worldwide, not just in the United States, UK, or Western countries worldwide, is about 5% of all those fatalities related to injuries. So not natural death or not sicknesses, just because there has been an injury before the death. And compare that 5% to 2%, which is what war causes. Most of these fatalities, these 5%, are actually not in Western countries. They are happening actually in developing countries, where actually we don't even learn that these people are dying because of fires. Again, most of these people are dying because of fires inside our homes, but fires at our homes, not wildfires. And this level of success in the number of fires that have been decreased is a nice story that we would like to keep happening in an accelerated way, but it comes with a high price, monetary high price. We're talking about billions, several billions in any single one of those countries where there is a success story per year. And that money could be used for something else, could be used for education, could be used for social security, could be used for developing better neighborhoods. But instead, it has to be used to protect us from fires. The same happens with wildfires. The cost of protecting or suppressing or fighting fires is also tremendously. And citizens worldwide demand better protection and more protection. And this is a role where science, fire science, combustion science, has a lot to help us with. When we think of how to protect us from the bad fires, these being from the outside, for example, a wild urban interface fire that is coming our way and is threatening people or their properties or the ecosystem, or a bad fire that is happening from the inside, we can think of how to arrange the protection in layers of protection. Some authors say there are 27 layers, some authors say there is only one layer. I happen to think, and my school of thought is Professor Dougal Drysdale from the University of Edinburgh, that there are 6 layers, at least 6 layers, and all other layers can actually be associated to other layers. The first layer, the single most important one, is not to have the bad fire. This is important because if it's a good fire, then the layer of prevention is to identify as soon as possible that it is a good fire and that you don't have to stop it. But if it's a bad fire and it has been identified as a bad fire, you have to prevent it, in the sense that do things before actually the fire develops. Make sure that it fails at the ignition step. Make sure that the fuels are not too dry. Make sure that the fuels are not too flammable. And make sure that the fuels don't find the ignition sources, etc. When the fire layer has failed, when we have failed preventing, there is a fire and the fire is ongoing, then the second layer kicks in, is detection. Because you have a watchtower, because you have a satellite, because you have a helicopter, because your neighbors are calling that they are seeing flames or smelling smoke. It doesn't matter how detection is arranged. The important thing is that detection happens as soon as possible so that we can start monitoring and following the progress of this bad fire. If it starts to get closer to people, where people live, then the third layer kicks in, which is very important, is to evacuate. If there is a fire, there is a bad fire that is propagating in the path of community, or if it's a good fire that is propagating in the path of a community, that community has to be evacuated, and that fire will always be bad. No matter that it might be healthy for the ecosystem, if there is a threat to life, then the fire, locally at least, should be declared as a bad fire. And you have to start evacuation of thousands of people. Maybe evacuation of just a few people, but it could be evacuation of parts of a town or parts of a city. It's a very complex endeavor. The fourth layer is compartmentation. The bad fire has been detected. There might be an evacuation going. The important thing is that the fire doesn't spread to other parts, to other forests, to other ecosystems, to other regions, to other parts of the town. Compartmentation in wildfires is also called very often as separating the fire with fire breaks, for example, or using rivers and roads as natural fire breaks. So it's the concept of having it in different parts and not allow it to burn across other parts. Then we have another layer, which is very famous, is the one that gets all the news because the images in fighting wildfires are impressive, is suppression. It could be the firefighters and the ground crews just beating the fire, or it could be helicopters or airplanes, air tankers dropping tons of water into the fire. Whatever form of suppression, this is a layer that comes towards the end when all the other layers have failed. When we have, in particular, we have failed prevention and compartmentation, is when suppression becomes more important. And the last layer is a structural resistance of the community or of the houses that we are talking about. Make sure that we don't lose the community, that the community is not completely wiped out, or we make sure that we don't lose the houses, that the houses are not actually burned. That is the last layer and the most desperate layer. And the protection, not just of buildings, but the protection of ecosystems can also be thought or understood and analyzed using very similar layers to the 6 over here. In this realm of protection, what is the role that we can have with fire science? Well, fire science is a discipline that creates new knowledge about fire. It allows us to understand better the many different aspects of fire. And then what do we do with this science? Well, because we are talking about bad fires or identifying fires from being good or bad, then we need to transfer this knowledge to society. There are many different ways how we can do that. This is actually something that scientists do very well, and engineers as well, and other practitioners and firefighters and emergency responders and authorities. But it is important that the science is not stuck in a library or in a book or in the hard drive of an academic or a student. It is very important that that knowledge gets to see the light of the day and that is shown in the best light as possible. So explain really what is it, the benefit of this knowledge, and how can it actually be used to save more people, property, and the environment. I just want to give you a few simple examples of what fire science provides. At the most fundamental level, for example, fire science allows us to understand what is a flame. What is a flame? So we all have seen flames. The great majority of us are tantalized and fascinated by a flame. But what is it? Well, we know a flame is a chemical reaction. The chemical reaction is actually combustion. There is an oxidation. And this reaction releases a very high amount of heat. It's a rearrangement of the bonds from reactants to products, and it produces a lot of heat because this heat is released in a very small region of space because flames are very thin. The volume in capture might be very large, but the flame itself is very thin. We're talking about literally millimeters that are separating the inside of the flame, which is where the fuel is, and the outside of the flame where the oxygen is. Well, because because the flame releases a lot of energy in that small region of space, it means that the gases get a very high temperature. They get temperatures in the order of 100 to 2000 Celsius, very high temperatures. They are so high indeed that the flame emits its own light by the process of thermal radiation. If they're not as hot, they actually will not emit light, but the flame is that hot. And that's why we see flames, and that's why flames glow, and they're actually so hot because of the combustion process. Now, what happens instants of time, fractions of a second sometime, right after the flame, right after the fuel and the oxidizer meet, and they release this heat? What happens right after? What happens right after is that the gas quickly cools down right after being a flame. Those atoms that are produced at the flame, they actually, sorry, not atoms produced at the flame, those molecules that are rearranged at the flame, they quickly cool down from very high temperatures. They might still be warm, they might still be at a high temperature, but it's not that high. They stop emitting light, and we call them smoke. So what is smoke? Smoke is what is the gas mixture, very complex gas mixture of different chemical species that used to be a flame. It could be seconds ago, or it could be that has traveled in the atmosphere for hours. But that the smoke is once upon a time a flame. Maybe it has mixed with surrounding air, it has been diluted, but we still call that smoke. And the main component of that smoke is what used to be a flame. What else can it tell us? Well, it can tell us about buoyancy. Buoyancy is this force that can move gases when there is a temperature differences and there is a gravity field, like for example on Earth. So they have this famous experiment by NASA where they lighted a candle, a birthday candle on Earth in the laboratories, and it looks like a simple candle, beautiful elongated going upwards. Inside the flame is hollow and is fuel coming from the wax, and outside is the air with its oxygen, and what they meet is the flame. And they did exactly the same candle light in microgravity inside the International Space Station, where there is no gravity. And you can see the difference between lighting in the absence of gravity and lighting in the absence of, so in the presence of gravity. There is oxygen as well here in the International Space Station. Astronauts breathe the air inside the International Space Station. So there is oxygen, there is fuel, but the flame is very, very different. It's very different in its color, it's very different in its size, it's very different in its shape. It's actually very different in its power. Indeed, in microgravity, flames they're not powerful at all. They're actually almost extinguishing themselves. Why? Because they don't have a preferential direction. There is no gravity. Therefore, the hot gases of the flame don't have a tendency to rise up as it happens in the flame on Earth. Then on Earth, because there is this upward displacement, that means that air has to be is dragged in and is entrained into it. And this actually is air that is helping the flame to keep burning more fuel. That mechanism of entraining and making air arrive to the flame doesn't exist. And actually the flame struggles to get enough oxygen because actually the oxygen has to move towards the flame at the same time as the smoke is moving away from the flame. So the smoke itself is actually displacing the oxygen away. If there were to be gravity, they will create this carousel that will actually bring the flame to a higher power. Why does it matter? Well, for example, it matters in wildfires because it helps us to understand why fires go faster uphill. That is a well-known fact of wildfire experiences, that a wildfire goes faster up the hill than when it's flat terrain, and actually even slower when it goes downhill. But why? And the reason for this is this little sketch that I did for my kids. I happen to like it a lot. Is that because of gravity, the flames are going upwards. They have a preferential direction, always going upwards. They like verticality. When they are vertical and uphill, the next layer of fuel that is going to be burning in the next few seconds is very close to the flame, such that it receives more heat and faster from the flames because this distance is significantly reduced. Whereas if it's flat, the distance between the next layer of fuel and the flames is larger and the heat arrives slower. Or in downward, the distance between the next fuel layer and the flames is even longer. And that simple fact, the distance between the flames and the next layer of fuel, because it's much shorter uphill, means that fires are much faster, significantly faster uphill than flat terrain, and even more than slope downwards. Another thing that fire science allows us to do is to understand why fuels ignite, why the wood, the needles, the leaves, the branches, the peat, or our houses made of wood or made of parts of plastic, why do they burn? And the reason for this is that if you have a fuel, there are many of them, natural or synthetic, is over here. If you expose it to a significant amount of heat, this could be a nearby flame that is arriving, or it could be a lightning strike, is an amount of heat. This amount of heat will actually start to heat up the fuel. The fuel will actually start to paralyzed. It will undergo a chemical reaction where it releases this white smoke with a very strong smell. This white, sorry, it's not a smoke, these white gases with a very strong smell. These gases are actually fuel in the gas phase. It will mix with the air, or it will have access to air, and it actually will form a flame. And the more heat it arrives, the more of the fuel will be converted into pyrrolysate, and the more it will actually lead to a flame. And that is the process that, thanks to fire science, we understand, which is very important, for example, to allow us to know what is the critical temperature, also called fire point, such that a fuel will start to sustain a flame. And below the fire point, below this temperature, the fuel might heat up, the fuel might partially decompose or char, but it will not sustain a flame. For wood, for example, wood materials is in the order of 350 Celsius. Plastics, it can be much higher. It could be actually 390. So it's actually in principle harder, not harder, but you need to bring the fuel to a higher temperature if it's synthetic than if it's actually a natural. In principle, you could say this over here. But this is just telling us at which temperature we have to bring our fuel so it can sustain a flame. If you are below, it will not sustain it. Above, it will sustain it. It doesn't tell us how difficult it is to get this fuel to that temperature, or how much heat do we need to get the fuel to that temperature, how fast we can take the fuel to that temperature. And this is something that fire science allows us to calculate, is the time to ignition. And this is at what time, seconds, does it take for a sample of our fuel, in this particular case is a polymer, if exposed to heat, for how long do I have to expose it to heat until it actually develops a flame? I know from the previous slide that the fire point of this polymer, for example, is in the order of 390 Celsius. But how long would it take to get there? And this is a process that is actually mostly governed by heat transfer. This is a very wide range of experimental data from this specific polymer. It's called PMMA. And this is a relationship between how long it takes and the amount of heat that is arriving. And what we know is that if we are above a certain threshold of heat arriving to our sample, then ignition can happen. If we are below, ignition cannot happen. There is the critical heat flux that is called. And as we increase the heat above that threshold, the amount of time that it takes, it actually gets shorter and shorter and shorter, to the point that, for example, an arriving flame, if the flame touches, literally touches, not just nearby, it touches a fuel, we are talking about heat fluxes in the order of 100 kilowatts per meter square. At that heat flux, it takes literally 10 seconds to ignite this polymer. If we were to ignite it even if we were to increase the heat flux even larger, to maybe actually have a bigger flame, we actually will be making ignition even shorter. But if we have flames that are nearby, but actually they are heating the fuel, but they are actually not touching it, maybe they are just 2 meters away, then the time that it takes to ignite is in the order of a minute and a minute and a half. So this relationship is very useful to know how long would it take my fuel, my house, my nearby fuel layer that is burning in a forest to actually start igniting and contributing to fire. And the time to ignition, for example, of biomass or wood, it is one of the characteristics of why would a fuel contribute to a fast fire or to a slow fire. Time to ignition, for example, if it's high, it will lead to slow fires, and a time to ignition that is short will lead to fast fires. So it's a very important principle to understand the speed of propagation, which leads us to the work of Rothermel, very important work of Rothermel. He did this in 1972. I was not even born, in the United States, in the US Forest Service, and it's an equation. They call it a model, but it's really an equation. The equation is over here. It has all these strange words, and I understand you can spend time looking into them. But the important thing of Rothermel is that this is a single equation. Most relationships are linear or actually inverse, proportionally inverse, right? All these at the top are linear relationships with the rate of spread, and these at the bottom are inverse relationships with the rate of spread. He was the first one to capture many, many years of experiments and theory of fire and combustion into a simple expression that could actually be understood and could actually be measured. He says the spread rate depends on the intensity of your fire, on the moisture of your fuel, on the amount of wind or the slope that you have, or the density of your fuel, on how effective is the heating to the fuel, or how much heat does it take to ignite your fuel. And that was a breakthrough. And it continues being a breakthrough. Actually, the work of Rothermel continues being used very widely all around the world, not just in the United States. And although there have been many attempts, no one has been able to put forward a model that has been proven to be better. There are opinions about new models that are thought to be better or are promised to be better, but we continue that promise. And since 1972, the work of Rothermel is literally impressive. Now, this expression, this simple expression, then can be put into a landscape model, for example, FarSight, and actually you have an ignition point, and it actually tells you what is the speed of propagation in the head of the fire, or what is the propagation in the front and the lateral fronts of the fire, or what is actually the propagation in the backward direction of the fire. So having this model allows us to actually calculate the speed and the form and the shape and the danger of a fire over the course of hours, and with complex shapes and complex wind conditions and slope conditions and even moisture conditions. It's a very effective, simple expression. And with this said, I'm just going to finish this short lecture, which is just an introduction. Hope I've given you enough information to just start the beginning, a wondering and a need and a motivation to know more. Just to remind you that fire is the greatest discovery of humankind, and both a human and anthropogenic hazard. That there are bad fires, which are a serious concern because of safety and because it can actually damage ecosystems. But there is such a thing as good fires, which are, some of them are good for the ecosystem. However, when a good fire for the ecosystem starts to threaten people and property, then that fire, at least locally, can be considered a bad fire. And the interplay between good fires and bad fires is very important for wildfires science. And safety is paramount to protect people, their property, and the environment from good fires or from bad fires. Fire safety is very important, and a better understanding. And there is a long way to go. A better understanding will enable innovation, will enable us to do things better and to find more solutions. And there is a lot that can be done to have a safer world. And I'm delighted to know that many of you have already done it and are planning to continue doing it and to help us all to be in a safer world. Thank you very much. Just want to finish to say thank you to my students and to my researchers and my sponsors, our sponsors, because without them, we would not be here. Thank you very much.